we're going to take a look at the idea in this section of something called an integral. An integral is this symbol, right? It actually is summa, and we'll learn about a little bit later as to why it's called summa, because we're going to sum up a bunch of things. But if we take the integral of any function, f of x, dx, okay, and I'll explain that in a moment, this is really, to evaluate this, this is just the antiderivative plus c, right? So now if we had this, the integral of f at y dy, that would be equal to the antiderivative of y plus c. And so this dy and this dx is just telling us which variable to take the antiderivative or the integral with respect to. Right now, later in maybe calculus 2 and calculus 3, you might start having other variables mixed together, and you would just treat those variables like constants. So an integral, really, to evaluate it, is just an antiderivative. Right? So just kind of get used to that idea. But the good news is that many of the rules, in fact, all of the rules for antiderivatives are going to hold true for integrals. So for instance, if we took the integral of something like two functions, let's say f of x plus g of x, and this is just an example, that would be equal to the integral of f dx plus the integral of g dx. Right? So you could just go ahead and distribute that. Or if for some reason you had the integral of the constant of a function, you could just go ahead and factor that constant out of the integral. Right? So, and these are rules that we're going to see throughout. But just letting you know that many of the rules, in fact, all the rules for antiderivatives are going to hold for integration as well, or integrals. So let's just evaluate integrals. That's what we're really just interested in this section, is just making sure that we can do a basic evaluation. And then when we move to chapter 5, when we start talking about the representation of an integral and what it really means, then we'll have those techniques tucked under our belts and we can just resurrect them. So let's just evaluate some general indefinite integrals. All right, and indefinite basically means that there's no numbers affixed to the integral or to the summa. So for right now, just worry about it being just an integral. All right, so, and of course we could check our work by taking the derivative. Now, the first thing we might wish to do is split this up into two separate integrals and then factor out the coefficients. So we can write this as 9 times x to the 17th dx minus 7 integral x to the 13th dx. And now we could just use our rules for anti-differentiation. So I'm just going to say this is the antiderivative, and this is the antiderivative of x to the 17th and x to the 13th, respectively. So this is going to be 9 times. Now remember, what we're going to do is we're going to add 1 and then divide by the new exponent. Right? So that's 9 times x to the 18th over 18 minus 7 x to the 14th divided by 14, and then plus our constant of integration, c. All right, so remember c was just a constant. Now we're going to call that a constant of integration. Right? Same thing as a constant of anti-differentiation. Right? We could certainly simplify this expression, right? Just because we know that 9 and 18 share a common factor of 9, and 7 and 14 share a common factor of 7. So this is going to be x to the 18th over 2. So that's an 18, sorry about that, minus x to the 14th over 2 plus c. And then finally, if we wanted to combine this, we could write this as a singular term. We could write this as x to the 18th minus x to the 14th over 2 plus c. All right, so this is one way to write the answer. This is another way to write the answer in a simplified form. This one might be the easiest one, right? And remember, this is our antiderivative, or the integral as well, right? So integrals and antiderivatives, they're essentially, to evaluate them, the same thing. Now, let's take the derivative of capital F and see if we get the same answer. All right, so I'm just going to take the derivative of capital F, and that's going to be 18x to the 17th divided by 2 minus 14x to the 13th divided by 2 plus 0. And then finally, this just becomes 9x to the 17th minus 7x to the 13th. Right? And that looks like the original function. So 9x to the 17th minus 7x to the 13th. Okay. So that looks like the exact same thing that we started with. A second example. Now this one looks a little bit uglier, and that's just because it is. Right? But the good news is we can just use the same techniques that we remember from differentiation. All right, so we have this 5 over root x plus 5 times root x. All right, so we're going to prepare it, and we're going to say that this is equal to the integral of 5x to the minus 1/2 dx plus integral of 5x to the 1/2 dx. Okay, or another way, if we chose to write that, is to factor the 5's out. So this could be 5 integrals of x to the minus 1/2 dx plus 5 integrals of x to the 1/2 dx. And then we're just going to evaluate. So now be careful with this, and I'm going to write this one out explicitly. So this could be 5x to the minus 1/2 plus 1 divided by minus 1/2 plus 1 plus 5x to the 1/2 plus 1 divided by 1/2 plus 1 plus a constant of integration c. Now we're going to simplify this, okay? We're going to have to use some algebra to simplify. So we get 5. Negative 1/2 plus 1 is 1/2. All right, and if you don't trust me, just go into your calculator. You can take negative 1/2 plus 1, enter, and then you can always use that trick where you hit math, enter, enter, and that gives you the 1/2. Okay, same thing with 1/2 plus 1. And then you can again do math, enter, enter to get 3/2. All right, so this is going to become, and in the denominator, you still have a 1/2. We're going to get 5x. We just did this in the calculator. 3/2 over 3/2 plus c. All right, now to simplify this, all right, there's a few things you'd have to do. Remember, when you divide by a fraction, you're really multiplying by the reciprocal. Okay, so we're going to multiply both of these to clean them up a little bit by 2 over 1, which is the reciprocal of 1/2, and 2 over 3, which is the reciprocal of 3/2. Okay. And then finally, we can write this one of a few ways. So 10x to the 1/2, because 5 times 2 over 1, plus 10 over 3x to the 3/2 plus c. Or one final way to write this would be 10 square roots of x plus 10/3 square root x cubed plus c. And that's the proper antiderivative of that function, or at least so we think. Now, how can we verify that? Well, we can just take the general or we can take the derivative of that integral. All right, so I'm going to delete this just to give us some room. And I'm just going to take the derivative. Now, what I'm going to do is I'm going to call this f capital. And let's just prepare it for differentiation. So another way to write f is to write it as 10x to the 1/2 plus 10/3 x to the 3/2 plus c. And now we can find f prime, the derivative. So that's going to be 10 times 1/2 x to the 1/2 minus 1 plus 10/3 times 3/2 x to the 3/2 minus 1 plus c. We know that 10 times a half is 5. 1/2 minus 1 is a minus 1/2. And then This just becomes 30 over 6, which is 5. 3 halves minus 1. Oh, by the way, this should be 0. Excuse me. X to the 1 half, and then plus 0. And then we could just rewrite that as 5 over root x plus 5 root x. And if you go back, 5 over root x plus 5 roots of x was the exact same thing that we started with inside of the integral. All right, so this is our correct antiderivative, which is the same thing as the correct evaluated integral. All right, so we'll take a look at a couple more examples in the next videos, but hopefully this gives you an overview as to how to evaluate something called an indefinite integral.